Bismillah ar-Rahman ar-Rahim. X and y are non-negative integers. We are interested in solving this equation. Factorial of x is equal to factorial of y times the factorial of y minus 1. We will make use of the following result. There is at least one prime number between x and 6x over 5 when x is greater than or equal to 25. Indeed, this result is more than what we need, and it can be generalized. So for x that is large enough, and for any epsilon greater than 0, then there is a prime between x and x times 1 plus epsilon. But this is what we need here. As usual, we start solving the equation by investigating the smallest non-negative integers. And we will see that xy equal to 0, 1, or 1, 1, or 2, 2, these three guys are solutions to the equation. For example, if we take 2, 2, the factorial of 2 on the right-hand side is equal to 2. And on the left-hand side, we obtain factorial of 2 times the factorial of 1, which is 2. The question is whether there are other solutions. Note that if x and y are strictly positive, then x is greater than or equal to y, because on the right-hand side, we have the factorial of x. On the left-hand side, we have the factorial of y times y minus 1 factorial. The power of prime factor p of the right-hand side, which is x factorial, is the floor of x over p plus the floor of x over p squared plus the floor of x over p cubed, and so forth. This is just Legendre's formula. And it tells us that the summation I from 1 to infinity of the floor of x over the prime number p to the power I, if we call this thing mu p of x factorial, then the prime number p, if we raise it to this power, then this is a factor of the factorial of x. So this divides x factorial. But if we increase the power by 1, then this is not a factor. We can apply the same formula to the left-hand side, noting that we have now the product of two factorials. Applying the formula to the factorial of y gives us that the power of the prime factor p in the factorial of y is floor of y over p plus floor of y over p squared, and so on. And then the power of p in y minus 1 factorial is the floor of y minus 1 over p plus the floor of y minus 1 over p squared, and so on. Now, the floor of alpha plus the floor of beta, so those are real numbers, is less than or equal to the floor of alpha plus beta. Now, this is because alpha is greater than or equal to the floor of alpha and is strictly less than the floor of alpha plus 1. And the same applies to the real number beta. If we add, then the floor of alpha plus the floor of beta is less than or equal to alpha plus beta, which is strictly less than the floor of alpha plus the floor of beta plus 2. So between these two integers, there are only two integers, right? The floor of alpha plus the floor of beta, and the floor of alpha plus the floor of beta plus 1. So this means the floor of alpha plus beta, which is here, can be this or this. So this floor of alpha plus beta is either equal to the floor of alpha plus the floor of beta, or it is equal to the floor of alpha plus the floor of beta plus 1. In both cases, the floor of alpha plus the floor of beta is less than or equal to the floor of alpha plus beta. We can make use of this to say that, for example, if we take these two terms, then the floor of y over p plus the floor of y minus 1 over p can be upper bounded by the floor of the sum 2y minus 1 over b. And we can do the same for the other terms. So now on the right-hand side, this is the power of prime factor p. And on the left-hand side, we have an upper bound on the power of prime factor p, which is given by this. So it must be the case that x is less than or equal to 2y minus 1 factorial. And there we have y factorial times something times an integer that is greater than or equal to 1. So x is greater than or equal to y when we focus on strictly positive integers. But now thinking about the power of prime factor p on the right and left-hand sides, we obtain that also x must be less than or equal to 2y minus 1. Because if x is greater than this quantity, then the power of prime factor b here on the left-hand side will exceed the power of prime factor b on the right-hand side. And we will not have equality, right? You have two integers equal to one another, then basically they have the same prime factorization, and the powers of the primes should be the same. So now we have a range for the values of x. If we hope to find another solution in addition to those ones obtained by experimentation and inspection, then x must be greater than or equal to y and must be less than or equal to 2y minus 1. Now we will divide into two cases, a case in which the integer y is even and another case in which it is odd. Suppose that y is an even integer. So y is 2 times m, and m is 1, 2, and so on. So now take y and replace it by 2m in this inequality. So x is between 2m and 4m minus 1. Now x is in fact not in this full range. It is from 3m to 4m minus 1. So we cannot take x to be less than 3m. Why is this? Because we have an inequality for the factorials. Here it is. That for every m that is greater than or equal to 2, we have that the factorial of 2m times the factorial of 2m minus 1 is strictly greater than the factorial of 3m minus 1. Why is this the case? This is an inequality that we can prove by induction. So if m is equal to 2, that's the base case, then we can compute the right and left hand sides, and we will find that this inequality is indeed satisfied. Now we assume that for some k greater than or equal to 2, we have the inequality satisfied, and we try to show that it is satisfied if we replace k by k plus 1. So if we take the left hand side and replace m by k plus 1, we will get the factorial of 2k plus 2 and the factorial of 2k plus 1. Factorial of 2k plus 2, that's 2k plus 2, 2k plus 1, and then factorial of 2k. And the factorial of 2k plus 1, this can be written as 2k plus 1 times 2k times the factorial of 2k minus 1. And so their product is 2k plus 2, 2k plus 1 squared times 2k, which is this one here. And then we have factorial of 2k times factorial of 2k minus 1. And by the induction assumption, this product here is superior to the factorial of 3k minus 1. So now this side is strictly greater than or equal to this side here. To finish our induction proof, we need to show that this is strictly greater than this factorial with 3 replaced by k plus 1. So we need to show that this product is greater than 3k plus 2 factorial. What we have achieved so far is that this product is strictly greater than this quantity here. We can write down this factorial as the factorial of 3k plus 2, and then what we have here is actually 3k minus 1. So to get 3k plus 2, we need to divide by 3k plus 2, 3k plus 1, and 3k. And those three guys here are the ones here. This is what we have so far. To be able to finish our induction, we need to show that this ratio is greater than or equal to 1. The numerator is greater than or equal to the denominator, or to show that the numerator minus the denominator is greater than or equal to 0. And this is what we can do here. We can take this guy minus this guy here living downstairs, and the difference between them will be this cubic polynomial. And in this cubic polynomial, and since we are interested in the range of k values, k greater than or equal to 2, this 5k squared is greater than 2. And we have here, if we focus now on this cubic term and this linear term, then 7k is strictly less than 7k cubed. Okay, and this is definitely less than 16k cubed. So the negative terms here are strictly less than the positive terms, and in fact, this difference here between the numerator and denominator is non-negative. So the ratio is greater than 1, and we have that 2k plus 1 factorial times 2k plus 1 minus 1 factorial. This is greater than 3k plus 1 minus 1 factorial, and we are done with our induction. So this inequality here will help us reduce the range of possible values of x. If x is 3 minus 1 or less, then what will happen is that the right-hand side, of the equation, so our equation is y factorial, y minus 1 factorial is equal to x factorial. Then the right-hand side, if x is less than or equal to 3m minus 1, can never be equal to the left-hand side, because the factorial of 3m minus 1 is strictly less than this product, the factorial of 2m times the factorial of 2m minus 1, by this inequality that we have obtained or demonstrated via induction. So our starting point is that x is between y and 2y minus 1. If y is even and is equal to 2m, then x is between 2m and 4m minus 1. Because of this inequality, x is between 3m and 4m minus 1. Will always be a prime between 3m and 4m minus 1. Our friend here tells us that there is a prime between x and x times 6/5. And what we have here is that we want to say that there is a prime between 3m and 4m minus 1. 4m minus 1 over 3m, that's 4 over 3 minus 1 over 3m. And this is greater than 6 over 5 when m is greater than or equal to 3. This means that there is a prime in this range, so long as m is large enough. And if we put m equals 2, let's see, 3m and 4m minus 1, if m is equal to 2, this is 6, and this is 8 minus 1, which is 7. So we have a prime. If m is equal to 3, then this is 9, and this is 11, and we have a prime. If m is equal to 4, then this is 12, and this is 15, and we have the prime 13, and so on. What does this mean? It means that on the right-hand side, x factorial, we have a factor, a prime factor between 3m and 4m minus 1. But on the right-hand side, we have y factorial and y minus 1 factorial. And y itself is 2m. So there can be no prime factor on the left-hand side that is greater than 2m. And so it is impossible that both sides will be equal. Let's recap what we are doing. We started with x between y and 2y minus 1. If y is 2m, that's an even positive integer, then x is between 2m and 4m minus 1. If x is less than 3m, then we have a problem, unless m is less than 2. And what is the problem? The problem is that if x is less than or equal to 3m minus 1, then the right-hand side of this equation, it has a maximum possible value of 3m minus 1 factorial. But this is less than 2m factorial times 2m minus 1 factorial. So based on this inequality proved by induction, we can say, well, perhaps x is between 3m and 4m minus 1. But between 3m and 4m minus 1, there is a prime. And so this prime will be a factor of x factorial, but it cannot be a factor of the left-hand side here. And so the only possible solution now, if y is an even positive integer, is that m is equal to 1. This is the only possible way to get a solution, to get an equality between the right-hand side and the left-hand side. If m is equal to 1, then y is equal to 2. And then we get the solution xy is equal to 2, which we already have by investigating the smallest non-negative integers. So the hope for another solution requires now that we assume that y is an odd positive integer. So we take y to be equal to 2m minus 1. And we will repeat the same steps. X should be between y and 2y minus 1. Now, if y is equal to 2m minus 1, then x is between 2m minus 1 and 4m minus 3. Can we have a solution in this range? If x is 3m minus 1 or less, we cannot have a solution to this equation. Why? Because in this case, the right-hand side will have a maximum value of 3m minus 1 factorial, which can be shown to be always less than y factorial times y minus 1 factorial when y is 2m minus 1. This is true for every positive integer m that is greater than or equal to 7. How can we show something like this? Again, we can show this by induction. There is no need to repeat the steps. It is the same essence as what we did for the previous inequality. Okay, so x cannot be 3m minus 1 or less. Perhaps x is between 3m and the highest possible value is 4m minus 3. Perhaps we can find a solution with x in this range. Also, perhaps we find solutions when m is strictly less than 7. So let's see, what about x in this range? Now this range, let's take the highest number divided by the smallest number. This is 4m minus 3 over 3m. 4 over 3 minus 1 over m is strictly greater than 6 over 5 when m is greater than or equal to 8. And in this case, this range here will be greater than the range that we have in our theorem. And so in this range, we are guaranteed to find a prime number. And for example, if m is equal to 7, if m is equal to 7 or more, we can find prime numbers. For example, if m is equal to 7, we have 3m is equal to 21, that's 3m, and 4m minus 3, that's 25. And between these two guys, there is the prime number 23. What does it mean? That x has a prime. Again, like in the first case when y was even, we have a similar situation. Now, if there is a prime number in this range, so the right-hand side will have this prime factor that is between 3m and 4m minus 3. But what about the left-hand side? The left-hand side is the factorial of y times the factorial of y minus 1, and y is just 2m minus 1. So we cannot have equality between these two sides because the right-hand side has a prime factor that cannot be on the left-hand side. So this means that this inequality, together with this fact, will make this equality impossible unless we deal with the small values of m. So m is any positive integer between 1 to 6. And for this range, we can just do it by brute force. When m is 1, we get a solution that we already have. When m is 2, it will not work because the product 3 factorial times 2 factorial is 12, and 12 is not something factorial. When m is equal to 3, again, we have failure. When m is equal to 4, and so y is equal to 2 times 4 minus 1, so y is equal to 7, then we get 7 factorial times 6 factorial, which is this number, and this number is exactly the factorial of 10. When m is 5 and m is 6, again, we will not get results. So there is, in addition to our 3 initial solutions, there is 1/4 solution, and the equation x factorial equal to y factorial y minus 1 factorial has only these 4 non-negative integer solutions.